Hello everyone. Previously we had discussed on the diameter of the tree algorithm, right? So today we'll be going with the LCA algorithm, least common or the lowest common ancestor algorithm. So basically one more thing I want to tell you here is we will be doing this one, will not be considering the recursion or the recursive DFS or the BFS for this. So we will be going with the this one, what do you call, binary lifting. You will also learn binary lifting along with the RMQ, right? Range minimum query. Queries will be given, so this is fine. So you will be learning two algorithms together. One is finding the LCA, so using mainly this one, binary lifting. If you remember one thing, we are done with the DP, solving the DP problems today. 50 DP problems we solved, right? So basically in the Codeforces, right? So if you remember, so we solved certain problems on basically this one, DP on trees, if you remember, right? We solved around some this one, maybe around 5 to 10 problems or around 5 problems, I don't remember exactly, but some problems we solved. This one we discussed on how to implement the DP on trees basically, right? So within that problem we had made use of the binary lifting for the extreme optimization, right? For the extreme optimization, also centroid, also we went with centroid calculation as well. That will be discussing in the future, no worries. So if you remember, we applied this one, what do we call, binary lifting. We used binary lifting on the trees along with the DP for the extreme optimization, right? For the queries, right? To solve this one, basically when we had to solve this one, basically when the queries were given, right? So to solve this one, what do we call, to solve the LCA queries and the big of logarithmic n time. So that's where we went with the binary lifting, if you remember, right? So this is the algorithm that we applied there, right? So let's see the same thing in the action, right? So what we will be doing, we will be calculating the lowest common ancestor. We'll be calculating again the lowest common ancestor using the binary lifting for the queries, for the range minimum queries, RMQ, right? So that's what we'll be doing basically. Don't get confused, right? So we'll not be making use of the recursion, so we can do that. We can calculate LCA easily. We don't have to go with the binary lifting. So this, we will be learning the binary lifting as well here. So that is the reason we'll be making use of the binary lifting here, main thing. So it is also one of the things, binary lifting is basically used to jump upwards quickly, right? So this is used, binary lifting term. So whenever, so I have made use of the binary lifting many times, basically. I wouldn't lie, when solving the trees problem basically, not only with the DP, while solving the DP problems for the extreme optimization purpose, right? Based on the basically for the problem, this one, tree problems, right? So I'll not lie. So what is it, the term binary lifting, what does it say? It is used in the tree data structures, right? So to quickly jump upwards by the powers of 2. When I say powers of 2, it may be 1, it follows in this path, 1 2 4 8 etc., right? 1 2 4 8 basically followed by this thing, same thing, ancestors, right? So its common use, basically binary lifting, its common use case is in lowest common ancestor. That's what we are finding here. Lowest common ancestor problems, kth ancestor queries, right? So this will be helpful, binary lifting will be helpful within the kth to find the kth ancestor queries as well, and other tree path queries, and other main thing, tree path queries, right? So the binary part, so the binary lifting is there, right? The term I'm making use of is binary lifting. The binary term, this part comes from using the powers of 2 jumps, using the powers of 2 jumps, which is similar to binary representation of the numbers, right? Which is similar to the binary representation of the numbers, but the application is purely in tree or graphs, not number theory, right? So this is fine, but the application of binary lifting is purely we will be making use of it on trees or graphs, right? So and the graphs problem also will be going with the binary lifting. So from tomorrow we'll be solving the problems on the graphs, right? So we are solving this one, we are discussing these kind of algorithms at the correct time basically, right? So this is fine, man, if you're following along with me. So now let's do one thing, let's get into the definition part. So the lowest common ancestor, LCA, of the two nodes is the in a tree is the deepest or the lowest node that is an ancestor of both nodes, right? Simple. I'll just read out this one loud. The lowest common ancestor, also LCA, of two nodes, right, in a tree is the deepest node that is an ancestor of both nodes, right? So this is fine, I believe. Using binary lifting, we pre-compute ancestors at the power of 2. Using binary lifting, what we do, we pre-compute ancestors at the power of 2, allowing us to answer LCA queries because of logarithmic n time. Allowing us to answer LCA queries because of logarithmic n time, right? So this is one of the this one important thing. Again, allowing us to answer LCA queries because logarithmic n time. Usually we make use of it this one for the extreme optimization purpose itself, right? So this is fine. Now let's move on with the explanation part. First, what we'll do, a tree with n nodes has parent-child relationships. We know this one, right? A tree with quite obviously with n nodes has parent-child relationship when it comes to tree. This we know. To find the LCA of two nodes, suppose let's consider u and v. To find the lowest common ancestor of two nodes u and v, we equalize depth. When I say we equalize depth, meaning we have to lift the deeper node upwards. Deeper node means the end node, right? Deepest node, deeper node upwards until both are at the same depth. Right? So that we need to do. First we equalize depth, then we have to lift together. Lifting together means, so we have to start from the highest power of 2, lift both nodes upwards until their parents match. Just remember this one. This is the same thing we'll be applying in the form of code, or will implement the same thing in the form of code or algorithm by making use of this one Python programming language. The final parent is nothing but the LCA. And these 2 points also I found this one very relevant, so I just want to discuss this one as well. So pre-processing also known as building, right? So building jump table up node of j is equivalent to the 2 to the power of jth ancestor of the node. That is done n because of n log n. Just remember this one. This is one of the important points, so I wanted to discuss, right? So and also querying is done in because of logarithmic n, right? So single querying, right? So we will be considering the queries for the input. So at that time we can discuss the same. So querying is done in because of logarithmic n. Just remember this one, right? Now let's try to implement or articulate the same thing in the form of code. This is fine, I believe, right? So now let's do one thing. Now let's start writing the code, right? So let's try to implement the same thing in the form of algo. First step would be, let's do one thing, let's import this is for the this one fast recursion limit. So we are going with the DFS, right? So let's set the recursion limit, right? So for the fast recursion limit, so I'll just go with here import sys. So this is fine dot, I'll just go with a set this one recursion limit, right? So set recursion limit. So how much? I'll just go with the 10 to the power of 6 month. This is fine. This is nothing but the exponentiation operator 10 to the power of 6. This is fine. Next step here would be, we have to build the adjacency list for the tree. Let's build the adjacency list for the tree. Suppose n equals 9. So this is fine. Let me give edges equals. So here let me go with 1, 2, 1, 3. Again let me go with 2, 4. Also let me go with 2, 5. This is also fine. Let me go with 3, 6. Also 3, 7. This is also fine. Finally, let me go with 6, 8 and also 6, 9. Right. So this is just building the adjacency list for the tree, right? So we are considering the edges here, don't get confused. So this is fine. The next part would be, let's go with the adjacency list representation, right? So I'll just go with graph equals here. So this is fine. Let me open one more, this one, square bracket here. So this one, let me make use of for loop. I'll just go with the underscore here. This one in range. So why this is not showing here in the range? So I'll just go with n+1. So because I didn't close this one here, that is the reason it was not showing, I believe. So if I give here, yep, now this is showing. This is fine for I in the range n+1, right? So now let me go with a for loop here, u comma v in edges. This is fine. So now let me give graph of u dot append here. So this one will append v. Same thing we'll be doing. Let's go with the vice versa. So I'll just go with v here. Let's append u here. So this is fine. Now let's do one thing. We have to initialize the variables, right? So I'll just go with log. Let me assign this one to the 15. Right, so this is enough for n less than or equal to 10 to the power of 5, since 2 to the power of 17 is greater than 10 to the power of 5 or 1e5, right? So that is the reason we are considering or we are assigning the log to 15. This is fine. Now let me consider uplifting. For the uplifting, I'll just go with the up. So this one initially, let me go with -1 into log, again for loop. For I'll just consider underscore in range. Again, we know the range n+1. This is fine. Yep. So this one basically up of vj we are considering, that is equivalent to the 2 to the power of j ancestor, right? So this is fine, man. Next, let me go with the depth here. Depth, let me assign this one to 0 into n+1. 0 into n+1. So this is fine, man. Now let's move on with the step 4. Nothing but we have to go with the DFS to fill the depth and 2 to the power of 0 and 2 to the power of 0. Nothing but the direct parent, right? So let me go with a function DFS here. DFS of I need v and t as parameters, right? So this is fine. Within the DFS function, so uplifting up I have considered. So this one will be up of v 0. Let me assign this one to p, right? So this is fine. The next step would be, let me go with a for loop here for I n, this time not the range. So I'll just keep here 1 comma log, right? So let me go with log here. This is fine. So within the for loop, let me go with if of v. So this one will be I -1 not equal to -1. Then what we will do, so this one will be up v. So this one will be I. This one will be up v I -1. This is fine. Again, so this will be minus I -1 as well. So now let's do one thing. Let me go with one more this thing, what do you call, for loop here. So this one for 2, let me make use of n. We have already written graph of v. Basically this is fine. So within this for loop, so let's write the simple if condition. If 2 not equal to this one p, then what we have to do, I'll just go with depth of 2 equals depth of where is this, depth of v plus 1 b plus 1. Finally, let's call the DFS here. Let's go on with the recursive mode here. DFS of 2 to v. So this is fine. We are done with the DFS part, right? So now what we need to do basically, so we have to go with the root or we have to root the tree at node 1, right? So I can just write it on this way, DFS of 1 comma -1. This is fine. this is fine. Now let's go on with the step 5, nothing but the LCA function. So I'll just go with the function LCA. So this one will be u comma v, this is fine. So within the LCA function, so let's make u the deeper node. If depth of this one u, if depth of u less than depth of v, this is fine. So here u comma v, v comma u, this is fine. Now let's do one thing. Let's lift u up to the same depth as v, right? So that's what we need to do accordingly with the explanation part, right? So that we discussed. So this one will be difference. So this one will be depth of u minus depth of this one v. This is fine, man. The next step would be, again, let's go with the for loop here for I in range this one log -1. Also we have to consider -1 and -1. So this is fine. So now if difference, let's make use of the right shift operator here. I this one bitwise AND operator. So this is not I, this is 1 basically, right? So this is fine. We are just lifting the u up to the same depth as v, right? So I can just assign u to up of u and we have to pass I here. This is fine. Yep. Now let's move on with the third step here. So what will be the third step? If after lifting we have lifted u up to the same depth as v, right? So now if after lifting, if u and v are same, then we have to return u in that case. So this one I can just write it in this way. If u equals v, then what we need to do, then we have to return u. This is fine. Yep. Next step would be, let's move on with the fourth step. We have to lift both until their parents match, in the sense for I and range. So this one log, yep, -1 comma -1 comma -1. So this is fine, man. Now let's do one thing. Let's go with the if condition. So if of this one u I not equal to -1 and up of this one u I, if it is not equal to of this one v, this one I, this is fine. U, let me assign this one to, so this one up of u and I, and again v, let's assign this one to the up of v and this one I as well. So this is fine, I believe. Finally what we will do, let's do one thing. Their parent is nothing but the LCA, least common ancestor, right? So we have to just return here up of this one u as well as the 0, right? So we are done with the coding part. Or the algorithm. So let's do one thing. Let's quickly make use of the example queries. So let's go with the example usage. Let's make use of the print for this one, interactive purpose, right? So this one LCA of let me go with 4 and 5, right? So this is fine, 4 and 5. I'll just show you the build, no worries. Just let me consider this one first. So I'll just go with 4 comma 5, right? So this one, let me paste this one 4 times, 4 or 5 times. This is fine. 4 is enough. So this one, let me go with 4 and 6 this time. Queries LCA of 4 comma 6, and the next one is LCA of 8 and 9, right? So let me go with here LCA of 8 and 9. So here let me go with LCA of, sorry, 1 second, LCA of 8, LCA of 9. This is fine. Finally let's go with the LCA of 5 and 9. So this is LCA of 5 and this is 9. this is fine. Now see here, one thing, let me explain the algo whatever we have written in simple terms, and then we can just run the code and discuss about the output, right? So this is fine. So what we have done here, first thing is we have set the recursion limit. That is the reason I have implemented SYS here, right? So we have set the recursion limit so that DFS, because DFS goes deep basically, right? The name itself says that it's depth first search, right? So we have set the recursion limit since DFS goes deep. So this is fine. Next, what we are doing here from this one, n edges, whatever I have considered this one from here, you can consider basically line number 33. So we are building the adjacency list to represent the tree edges, So this is fine. Now after that, we are pre-computing the up this one node j, where each cell stores the 2 to the power of jth ancestor of node. We have discussed this one. Next, we have written the DFS helper function, right? Helper function. This one is nothing but DFS fills the depth and the parent table. What it does, it fills the depth and the parent table. Then we are going with a function LCA, the last one. What we are doing here, LCA of the parameters u comma b, whatever I have considered here. So this bring both nodes to the same depth. That's what we did first, right? So difference this one, right? So this is fine. Next, we are moving them upward simultaneously until parents match. Then we are returning the parents as the LCA. Right? So this is how we have written the algorithm. So this print, this is nothing but the example usage. Let's see that one now, right? So I hope the algorithmic part is completely clear. How we have made use of the binary lifting, why we have made use of the DFS, and why we have set the recursion limit to 10 to the power of 6. So these kind of things, or this thing, I shouldn't come in your head. So I have explained most of the things step by step, and this has to be crystal clear by now. Or the algorithm has to be crystal clear by now, right? So now let's discuss the output of the code basically, right? So let me show you the this one, what do we call what we have considered here, basically the build of the tree, basically the example that I have considered here, right? So this one 1 2 1 3 2 4 2 5. So this one basically we have considered the queries 4 5 4 6 basically, right? So let me show you the build of the tree first, then we can consider this one, right? So first here we have move this one, 1 second, just give me a second here, it's just right. So 1 2 1 3, so 1 second. So this one has to be 1, this one we have 1 2 3 as well, right? 1 to 2 1 2 3, this is fine. Next we have 2 to 4, basically 2 to 4 is fine. Then we have 2 to 5 as well, right? So this one, don't think 2 to 4 we have, 3 to 6 we have, wait 1 second, 3 to 6 we have, this is fine. And 3 to 7 also we have, 3 to 6 and 3 to 7. Finally we have this one, what do we call, 6 to 8 and 6 to 9. 6 to 8, this one is 2 to 5, finally we have 6 to 8 and 6 to 9, right? So this is fine, I believe, 6 to 8 and 6 to 9. So this is the edges we have considered, right? N equals 9 basically, right? So 1 2 3 4 5 6 7 8 9 10, or 0 to 8. So n equals 9 we have considered, right? So this is level, this is level. So now let me tell you one thing here, just give me a second here, this is fine. So we have considered LCA of 4 and 6, right? The first one, for the first one we have considered, sorry, LCA of 4 and 5. So this one 1 2 3 4 5 6 7, finally from 6 8 9, right? Just you can just pause the video and you can just see this one, this is fine. Now let's come to the input output part. So this one, right? So we are going with the LCA of 4 and 5. So let me draw this one here itself. I just wanted the reference basically, sorry, 1 2 3 we had, for this one we had 4 5, and for this one we had 6 7. Finally 6 had 8 9, right? So if I remember correctly, this is fine. Now LCA of the 4 and 5 here, LCA of 4 and 5 is this one, right? 2, least common ancestor, common for both 4 and 5. This one is 2, right? So the output that we need to get here is, for this one we have to get 2, right? So LCA of 4 and 6 we have. So LCA of 4 and 6 we have. 4 we have here, 6 we have here, right? So both are the leaf nodes of this one, different ones, right? So this is the leaf node of 2 and this is the leaf node of 3. So the least common ancestor for these two is not, either it cannot be 2 or it cannot be 3, right? So we cannot give 2 or 3. The least common ancestor for this one is root 1, right? So the output has to be 1. For this one, lowest common ancestor of 4 comma 5 is this one, what do we call, 2. The lowest common ancestor of 4 comma 6 is nothing but 1. Next we have lowest common ancestor for 8 and 9. For 8 and 9, see here, for 8 and 9 we have the least common ancestor 6, this one. This is the leaf node. 8 and 9 are the leaf nodes of 6. So the lowest common ancestor would be 6 itself, right? So 6 itself. So for 8 comma 9 we have the lowest common ancestor nothing but 6. The last one, least common ancestor or the lowest common ancestor of 4 and 5 of 4 and 5 is nothing but this one, 5 comma 9. We are going with this one, right? Lowest common ancestor of 5 and 9, basically 8 and 9 we considered. Finally this one, what do we call, 5 and 9. 5 and 9, 5 is here, 9 is also, 9 is here, right? So this one, basically it is the leaf node of 6 and the 5 is the leaf node of 2, basically 5 is the leaf node of 2. So the lowest common ancestor for these two is 1, again the root 1. So lowest common ancestor of 5 and 9 is also 1. So the output that we need to get here is 2 1 6 1, right? So the output that we need to get here is, lowest common ancestor of 4 comma 5 is nothing but 2. The lowest common ancestor of 4 and 6 is nothing but 1. Lowest common ancestor of 8 comma 9 is nothing but again 6, and the lowest common ancestor of 5 comma 9 is 1. So the output that we need to get here is 2 1 6 1, right? I hope this part is completely clear, man, right? So this is fine. Let's do one thing, let's run the code. So let me copy this one entirely, and one more thing, explanation is same, explanation goes same for all the algorithm. If you guys are this one practicing in the Java, right? So I can just check the Java code as well. So I do practice on the Java itself first, then we'll come to the Python most of the times. So here I do practice on the Java. You can just check the Java code. The explanation remains same. Way of writing the code becomes somewhat this one, syntax and other stuff, right? So Java is little bit lengthier. Writing the code in Java will always be a little bit lengthier, right? Not a little bit lengthier, it's lengthier, right? So syntax, we have heavy syntaxes on the Java basically, right? So this is fine, I believe. So now you can just check the code in the Java as well. If you are practicing in the Java, it doesn't matter, the programming language doesn't matter, right? First I used to do with the JavaScript or the Java. Now I am doing with the Python or the Java. First main language I consider here, this one, Java, basically, right? So Java or the Python we are going with. So now we have the idea what output that we need to get. I have shown you. So this one, let me run this one very quickly, right? So let me give here Python followed by the file name .py. So we have some error here in the line number 35. What is the error? List object is not callable. Graph of u dot append of v. This one in the line number 35, right? So let me come to the line number 35 here. What's wrong here? This is fine. Append of v, graph of v, dot append of u, right? So this, oh, this one has to, we have to represent this one in the array, right? So that is the reason it is screaming. So now let me give clear screen here, and yep, LCA of 4 and 5 is 2, right? And LCA of 4 and 6 is 1, we have discussed this one, 2161, right? LCA of 8 and 9 is 6 and LCA of 4 and 5 is 1, right? So LCA of 4 and 5 is nothing but we are considering the nodes 5 and 9 from this one, 4 and 5 basically, right? So this one is 9. So now we have the desired output, meaning whatever the algo that we have written works absolutely correct. So this is written because to make use of the so I wanted to show the binary lifting, how we make use of the binary lifting as well along with the algorithm. So this is used in the extreme optimization, binary lifting, right? So for the queries, when we have the queries, right? So when we are dealing with the queries, especially and the trees problem, right? So again I am telling you what's binary lifting here, why we are making use of the binary lifting here. So binary lifting, basically it is the tree data structures, it is used in the tree data structures to quickly jump upwards by the powers of 2, right? So powers of 2 in the sense 1 2 4 8, right? In that way, ancestors. So its most common use case is an lowest common ancestor. So this is the algorithm that we have written, it's right in front of you, and its use case in the lowest common ancestor LCA problems, kth ancestor queries, and the other tree path queries. This is fine. The binary part comes from using part of powers of 2 jumps, which is similar to the binary representation of the numbers, right? But the application is purely in trees or graphs, not the number theory. But the application is purely in trees or graphs, not the number theory, right? So this is it for the basically LCA algorithm, least common ancestor algorithm, right? So next what we will be doing, we will be discussing on the this one, validating the binary search tree, right? So let's we have two algorithms basically based on the binary search tree. One is validating binary search tree or converting the sorted array to binary search tree. The next one is balanced binary search tree conversions, whether it may be AVL, whether it may be red black, whether it may be tree, right? So this thing, these two things, these two algorithms are based on BST. So it is indirectly it is based on the this one, it is tree algorithms, right? Validating BST or converting the sorted array to BST and balanced BST conversions. Then we can hop into the segment tree and other stuff, right? Fenwick tree, centroid decomposition, and other this one, Euler 2 techniques, square root decomposition on trees, those things, right? So now next we'll be discussing on the validating binary search tree or converting sorted array to the binary search tree algorithm, right? So now we are done with the LCA algorithm using binary lifting, right, for the queries. So for now this is it. Thanks for watching.